Cool, thanks. All right. Hi, everyone. I'm Fabio Pacucci from CFA. This is another talk on the little red dots, but a little bit more on the theory side. So at the end of this presentation, I hope that you will be convinced that the little red dots are real masters of disguise in the distant universe. So as Guillermo said, the little red dots are very red and compact high redshift sources. They were detected by JWST about 3 years ago. And I just want to remark a couple of properties that are very important for the little red dots. First of all, answering also James' question a few minutes ago, they are characterized by abundances that are intermediate between those of UV-selected quasars and standard galaxies. So they're about 1% of the standard Lyman break galaxy population. And also the bulk of their redshift distribution is between 4 and 8, so they are very visible during about 1 billion years of cosmic history. So what are they? Well, we know that they are compact. Typical effective radii are 100 parsec, and there are typically two physical interpretations to explain what powers most of their light. Either they are AGN dominated or they are star formation dominated. Both interpretations come with caveats. In the first case, black holes seem to be overmassive with respect to the stellar mass, and they're also X-ray undetected. In the second case, the implied stellar densities are extreme. So since this is a galaxy conference, I will briefly mention the stellar densities problem because I think it's very relevant for this conference. But then I will describe a simple theoretical model that we put out a few weeks ago to explain a simple way the physical origin for the little red dots. In particular, we propose that they are descendants of low-spin halos, and in particular, this model allows us to explain 3 key observed properties of the little red dots, so their abundance, their compactness, and their redshift distribution. But let's start briefly from the stellar density problem. So in the star-only interpretation, you need so many stars to reproduce the UV brightness that given that they are very compact as well, some of the little red dots are estimated to have extreme stellar densities at the core. So just how dense are they? For the most extreme ones, imagine to take the entire Milky Way galaxy and squeeze it, making its radius about 50 times smaller. So with an undergraduate at the CFA and also Dale Kocheski from Sears, we studied the largest sample of photometrically detected little red dots from Cosmos Web and Primer, about 500 of them. And in this plot, you can see the probability distribution function of their core density, so calculated in the innermost 1 parsec. So in particular, about 35% of them have implied stellar densities that are higher than the highest stellar densities measured at the center of globular clusters. So just to make you feel how dense the most extreme little red dots are, there is the same difference between the stellar density in the solar neighborhood and the stellar density in the highest density little red dots, as there is a difference between being alone in this room or having the entire population of China in this room. So this is approximately the difference. So we're investigating this problem with 3 complementary approaches from a dynamical perspective. So we want to understand if the extreme stellar densities will lead to core collapse. So I don't want to go into too many details in this, but for example, with a detailed direct N-body simulation about 1 million particles, we witnessed the formation of a very massive star at the center via stellar collisions with a mass of above 10 to the 4 solar masses. And in general, these 3 complementary approaches indicate the formation via stellar collisions of a very massive star between 10 to the 4 and 10 to the 5 solar masses. Also, this very massive star will soon collapse into a massive black hole of approximately the same mass. So being a black hole guy, my punchline is that a black hole in the little red dots is pretty much inevitable, even if you try not to put it at the center. So let's move to the actual main part of the talk, so the origin of the little red dots in low-spin halos. And in particular, our model makes 2 main assumptions. First, the galaxy size, so the effective radius, is proportional to the spin of the dark matter halo. So a high spin halo yields a large galaxy, a low spin halo, a much smaller compact galaxy. Second, we assume that the spin values follow a log normal distribution, so very low spin parameters are exponentially suppressed. Now, let's assume that the little red dots are simply galaxies that form in the lowest 1% of the spin distribution. So they are both compact and rare by constructions. So with that simple assumption, we can reproduce the two key observed features of the little red dots at redshift 5, so the median redshift of the distribution. So in this plot, on the horizontal axis, you see the effective radius, so how compact they are. On the vertical axis, you see the number density, so how abundant they are. The color scheme, the color indicates the spin of the halo. And the shaded region here, you see the observed range of the little red dots. So our model that connects the number density to the effective radius naturally passes through this region. So low spin halos produce compact galaxies that are also pretty rare by construction. And also we show in this plot that the same theoretical model can explain the redshift distribution of the little dots. So why are they peaked approximately at redshift 5? So the red curve here shows the predicted fraction of galaxies from the general population of galaxies that are as compact as little red dots as a function of redshift. So this increases because at higher redshift, it's easier for halos to produce small galaxies. The blue curve shows the average surface brightness of that little red dots as a function of redshift. So these galaxies, of course, become fainter at higher redshift because of cosmological dimming. So in general, we see three different redshift regimes. At low redshift, the little red dots are bright but extremely rare. At higher redshift, they are very common but also very faint, so hard to detect. So in between, approximately between redshift 4 and 8, we enter the little red dots era. So when these galaxies are both common and also bright enough to be detected. And also I wanted to briefly mention that yesterday UC-HiPACC showed in the paper by Tanaka the redshift distribution of the fraction of the little red dots, and the shape of that observational derived distribution is basically log normal, so it's exactly as this line. So I think this is a very nice confirmation, or at least supporting this theory from observational side. And he also, of course, tested this model using other observational constraints that were available about 1 month ago. So in this plot, we show the relative number density of little red dots normalized at redshift 5. The black line is our model, and data points go from 7.5 in redshift to 2.5. So as you can see, our model reproduces the observed decline pretty well, and around redshift 7, the surface brightness correction becomes very important. So in the last couple of minutes, I wanted to highlight a new beautiful paper by Rinaldi, in which we put into practice, basically, the calculations for the surface brightness dimming that I just mentioned. So in particular, we find little red dots at redshift 2. It's named the saguaro. And on the left, you see the galaxy, and it has a very bright core, and it's surrounded by like a bluer outskirts. So on the right, this is the near spec SCD. You can see the classic canonical V shape for the little red dot. And in particular, it's very important to note that the V-shape SCD is only visible at the core of this galaxy. So if you go in the outskirts, the V-shape disappears. So at this redshift, at redshift 2, the disk is very visible because it's pretty close in redshift. But as you step farther back in time, this low surface brightness temperature will progressively disappear. So in a little bit of a romantic or nostalgic vibe, we wondered what this galaxy would have looked like when it was young. So we built a simple time machine, and on the left, you can see the actual observed galaxy. galaxy. And on the right, we simulated what it would look like at Redshift 7 using basic cosmological dimming calculations. So basically, as you can see, only the compact red core remains, and the whole remaining outskirts completely disappear. And at Redshift 7, this is basically indistinguishable from any other Leroy dot at Redshift 7.5. This is from the JADES survey. So this is my last slide, and I also wanted to briefly follow up on the discussion on the panel that we had yesterday about the Blumenthal et al. 84 paper. So as I mentioned yesterday, on the left, there is the figure 4 from the Blumenthal 84 paper. So horizontal axis is the virial temperature, vertical axis is the total mass. So if you make the calculation, Leroy dots are pretty standard in this plot. So they fall exactly on the Faber-Jackson ridge. So this tells you that the dark matter halo for the Leroy dots is pretty much how the 84 paper, the basic of cold dark matter model suggested. But if you go on the right, so this is figure 3 from their paper, horizontal axis is the virial temperature, vertical axis is the baryon density. As you can see, normal galaxies are very close to the cooling lines, as we discussed yesterday, but the Leroy dots are much, much lower, several orders of magnitude lower, meaning that their baryon density is much higher. So if the dark matter halo for Leroy dot is as expected, the outcome in this case is not expected. And in addition to what I said yesterday, I also calculated a few hours ago, basically how the spin parameter impacts the location of this population of galaxies in this plot. And as you can see, as you decrease the spin, the whole population shifts towards the left and bottom. So this is telling you that this particularly peculiar population of galaxies may undergo to very large compactness, so dissipation is increased, and in general you can go to a phase in which the cooling is much larger than what was expected in the 84 paper. So in short, the 84 paper told us where galaxies form, but the Leroy dots may be teaching us that baryons can actually much over collapse over this region. So in this case, rare halos may lead to very rare galaxy conditions. And I'll conclude here. Thank you.
Thank you, Fabio. I think we have time for maybe one question. And can I ask the next speaker to come up and get set up? Hand in the back.
Very nice. I wonder, so can you go back to a time machine?
Yeah.
So the Redshift 2, if I may say, it's a ringed nugget galaxy, right? If you simulate it to Redshift 7, you have a red nugget.
The Redshift 2 is what?
So, okay, so just to focus on Redshift 7, the red nugget there, is it spatially resolved or is resolvable by JADES? I think the key feature of little red dot is that it's not resolved, right? There is no resolvable.
No, some of the Leroy dots are actually resolved. Yeah, they are above the PSF. Yeah. Also, some of the Leroy dots are even at Redshift 7. You have several examples of Leroy dots that are imaged, and so they are actually spatially resolved. Yeah.
Okay. Let's get set up here, and I'll take one last question from Mark.
Yeah, thank you very much for the nice talk. Just a clarification, because I'm a bit confused. So you show that your model clearly reproduces the compactness of these objects when you assume that the dark matter halos are low spin. But then you're showing this Redshift 2 galaxy, which actually, in fact, is not that compact. It's just you claim that there's a disk and that you might be missing it.
Yeah.
So how do you reconcile both? So because at the end, you don't need that compact.
So you're talking about the low spin. Yeah. So basically, it's possible that in the Redshift universe, these galaxies are generated from very low spin. So you are generating most of the star formation at the center because everything is very compact at the center. But then you start to build up star formation in the outskirts. This star formation is bluer. So this makes progressively disappear the V-shaped SCD that actually characterizes them at higher redshift. So the low spin will induce most of the star formation at the center because it's low spin, so it's compactifying everything. But then later on, you start to form bluer stars in the outskirts, and you get out of the selection criteria that Guillermo was describing before. Yeah, I would say so. Yeah, and actually there are several papers that are suggesting this. There is a Billand paper a few weeks ago.
Okay, let's thank Fabio again.